All right, let's jump right into Section 1, the purpose of Method 201A, or as we like to call it, the challenge of invisible villains.
So, Method 201A was developed by the US EPA for one very specific job, measuring filterable particulate matter. We're talking about materials that are solid or liquid at stack conditions, specifically those with a nominal aerodynamic diameter equal to or less than 10 micrometers, that's our PM10, and 2.5 micrometers, which is PM2.5. To put that into perspective, right, a single human hair is about 70 micrometers thick. So we are hunting for incredibly tiny particles here. The method uses in-stack sizing devices to physically separate these particles right out of the gas stream. Now, just a quick reminder, if you also need to measure condensable particulate matter, the stuff that only forms a solid or liquid after it exits the stack and cools down in the ambient air, you'd have to pair this up with EPA Method 202. But for the filterable, in-stack component, Method 201A is your go-to.
Now, Method 201A fundamentally differs from the old, reliable standard, Method 5. If you've run Method 5, you know the whole game is operating isokinetically, right? You're constantly tweaking your flow rate so the gas velocity entering your nozzle perfectly matches the stack gas velocity. But Method 201A, it totally flips the script. It uses a constant sampling rate. And why is that? Well, because Method 201A relies on actual physical in-stack cyclones to separate the particles by size. The pure physics of those cyclones absolutely demand a constant, steady flow to maintain those precise size cuts at exactly 10 and 2.5 micrometers. If you mess with the flow, you change the cut size, and boom, your data's ruined. So Method 201A trades that strict isokinetic adjustment for physical particle sizing. You're aiming instead for a steady flow that lands at an acceptable 80 to 100% of isokinetic flow. Moving right along to Section 2, Equipment and the Cyclones. This is your arsenal in the stack. At the absolute heart of this method is Cyclone IV. This is the device responsible for sizing those tiny 2.5 micrometer particles. These cyclones are usually made of stainless steel or sometimes high-temp specialty metals like Inconel if you're working in really extreme stock conditions. But the massive takeaway here is the absolute uncompromising precision required. We're talking about physical interior dimensions. The inlet diameter, the cup height, the cone angles, they have to be machined to within a tolerance of plus or minus 0.02 centimeters. That's incredibly tight. The air enters the cyclone, it starts spinning, and physical centrifugal forces just drop the larger particles into the collection cup at the bottom, while the smaller PM2.5 particles are carried right up through the top and catch onto the filter. This precise physical separation is exactly why your flow rate has to stay absolutely constant. Okay, Section 3, Pre-test calculations and setup. Before you climb, you need a strategy. Take a look at this chart. It's basically a stack tester's map to success. Remember, we have to keep a constant flow rate to satisfy two completely different cyclones at the exact same time. Cyclone I for the PM10 and Cyclone IV for the PM2.5. To get accurate particle cuts for both of them, your chosen sampling rate has to land perfectly within that visual overlap zone you see here. It's the space perfectly balanced between the required cut size lines for both cyclones. Finding this sweet spot isn't guesswork. It requires preliminary data right from the stack, like temperature and gas composition. It's honestly a really delicate balancing act of fluid dynamics before the actual test even kicks off. Getting to that optimum sampling rate follows a pretty rigorous mathematical progression. First up, you've got to determine the stack moisture and estimate your PM concentration. You need to make sure you sample long enough to actually collect a weighable mass. Next, you calculate the initial gas stream viscosity and flow rate, and that's based on your preliminary temperature and velocity traverses. Step 3, you pick the right nozzle size. You're looking for a nozzle that lets you hold that constant sampling rate while staying as close to 100% isokinetic as humanly possible. And finally, you calculate the orifice box pressure drop, which we all know as delta H. This delta H is the exact target you're going to lock into your control box during the test to guarantee that steady flow. Now, real quick, before we actually climb the stack to execute this test, if you're a focused learner studying for your QSTI exams, or you're just trying to navigate these really complex source testing protocols, make sure you subscribe. Actually, better yet, just send an email to qstiprepacademy@gmail.com. Seriously, qstiprepacademy@gmail.com. If you reach out there, you'll get full, in-depth explanations, comprehensive study guides, and formula breakdowns that totally demystify these exact procedures. It is, hands down, the best way to get the comprehensive resources you need to pass. All right, let's get back to it. Section 4, Sampling Procedures and Execution. We are heading into the field. The physical execution of Method 201A is highly structured. It all kicks off with a strict pre-test leak check. Your entire sampling train cannot leak more than 0.02 cubic feet per minute or 4% of the average sample flow, whichever is less. Because think about it, a leak means you aren't pulling the exact volume of gas you think you are, which completely wrecks your constant flow rate and, by extension, your particle sizing. Once you're sealed up, you execute the test by traversing the stack. Now, unlike Method 5, which might have you hitting up to 24 points, Method 201A recommends a maximum of 12 traverse points just to keep the sampling manageable, and you have to dwell a minimum of 2 minutes at each point. You've got to hold that constant flow, keeping a super close eye on your manometer, and you really only adjust if the stack temperature swings wildly. And when you're finally done, you do a mandatory post-test leak check at the highest vacuum you achieve during the run just to prove your sample's integrity.
Section 5. Sample Recovery and Analysis. Time for the aftermath. Recovering this sample seriously requires the precision of a surgeon. We use 5 very specific containers to cleanly segregate the particulate by size. Container 1 holds the actual filter with the PM2.5 catch. Container 2 is your acetone rinse of the nozzle and the Cyclone eye catch, so that's your larger particulate stuff greater than 10 micrometers. Container 3 is the acetone rinse of the Cyclone eye outlet and the Cyclone IV inlet, giving us that middle ground particulate between 10 and 2.5 micrometers. Then we have Container 4, which is the acetone rinse of the Cyclone IV outlet and filter housing. That gives us the rest of the PM2.5 catch that, just didn't quite make it onto the filter paper. And finally, Container 5 captures the cold impenger water for your moisture calculations. You're using specific nylon or fluoropolymer brushes and acetone here to make sure every single microgram of particulate is quantitatively transferred without any outside contamination creeping in. And that brings us to our final stop, Section 6, crunching the final numbers, the verdict. Back in the lab, after meticulously desiccating and weighing our samples down to a constant weight, we run through a series of formulas to reach the ultimate goal, Equation 47. To figure out the quantitative recovery of filterable PM2.5, we combine the mass from Container 1, that's M1, your filter catch, with the mass from Container 4, which is M4, the acetone rinse of all the PM2.5 Cyclone hardware. We add those up, apply the necessary unit conversions, and divide by the total dry gas meter volume sampled, properly corrected to standard conditions. I know it looks like a simple equation on the surface, but it's really the culmination of intense fluid dynamics, incredibly strict field execution, and pristine laboratory gravimetric analysis. As we wrap up this explainer, I really want to leave you with a crucial thought. EPA Method 201A is basically a marvel of applied physics. It uses mechanical cyclones to perfectly separate invisible particles suspended in scorching, turbulent industrial exhaust. And the whole thing hinges on that one absolute golden rule, maintaining a constant sampling rate. So given the stringent math, the insanely tight machining tolerances of the cyclones, and the totally unforgiving environment of the stack, how confident are you in the precision of your constant sampling rate out in the field? Because getting it right isn't just about passing a test, it's about providing the true, accurate data that actually protects the air we all breathe.